So let's start. Are you ready, Marcus?
Hello. Yeah, I'm ready.
Hello, everyone. Welcome to this webinar. We are presenting today the webinar with the name Designing Common Mode Jokes. It's a bit of a special webinar because we show you something that we developed in the last few weeks, months internally, but have not yet released to Frenetic AI. So it's something that we also ask for a bit of feedback at the end to see whether we are on the right track, and if everything is successful, we will release this tool in the coming weeks, month, something like this. Before starting, I would like to share something. Let me share the screen. You should be able to see now the screen. So basically, we developed it. Many of you might know, but maybe not everyone. We have developed a new software package. It's called Frenetic AI. It's kind of an AI tool that helps you to design a power electronics converter. Let's say you start a tool, you can choose your topology. Here on the example of a CLLC, we put in the parameters, press a button, and then the tool completely designs the schematic of a power electronics converter, in this case a CLLC. You can also download LTSpice or Plex files, so you have quite some flexibility to then continue working with it. And one thing you can do is you ask the tool to suggest a magnetic design, and then the tool calculates you or designs an optimal magnetic for your purposes. In this case, even with an integrated leakage inductor that is used as the series inductor. This is a new tool, and it kind of completes our existing tool, which is called Frenetic Magnetic Simulator, which many of you might know. This is kind of our old tool. That's the tool that allows you to optimize and design magnetic components. So in this case, I automatically uploaded the magnetic component into this tool, and I can continue working with it. This you will have access for free, at least temporarily, if you go to the website app.frenetic.ai. I will share it in the chat. You can register, and then from there you can make a login and work and try out the tool. And yeah, so I share the link to this website that I was just showing. But today it's not about this tool. Today it's about designing common mode jokes. So this is a feature we have currently not in our toolbox. So it's not something we offer, but Marcos in the past 3, 4, 5 weeks designed a new way of designing common mode jokes. And it's something we would like to show you. And ideally, this will then be integrated in Frenetic AI and Frenetic Simulator. Okay, like this, I would start with the actual presentation today. Can you see now the screen, Marcus? Okay, is it?
Yeah.
I'm sharing the right screen. So, okay, so we have a small presentation about common mode jokes. First, I would like to give a very brief overview about the theory of common mode jokes and why is it difficult to model or why is it difficult to design common mode jokes, and then Marcus takes over and makes a little demo with a tool that we have developed. So first of all, what is common mode current in general? If you have a switch mode power supply, like here, for instance, shown, where you have the components and you have the switches, and when you switch, usually what one considers is the so-called differential mode, so the current that flows. Let me take the laser pointer here, that flows out of the source and back into the source. So it's kind of a circle. But if you have parasitic elements, like let's say like a capacitive element, which can be from the semiconductor to the ground, something you don't actually want, but it's always there, and you have switches, then there is a path for the current to flow through this capacitor. And because of this, you will have a current that flows on the positive side as well as on the negative side in the same direction. And this is called, these are called common mode currents. This is something you always have, and especially in switch mode power supplies, this is problematic and can disturb neighboring systems. Because of this, there are rules you cannot have too much of this common mode current. So far, so good. This is just another picture showing the same. You see here, this is the converter, and here illustrated are the common mode currents in path in red and the differential mode path in blue. Now you have to quantify this common mode current as well as differential mode currents, and for this there is a standard way of doing this. You use something called LISN, or line impedance stabilization network. So it's kind of a default equipment that you connect between the power supply and your converter, and it always consists of the same components. And now when you think about this, if you have a common mode current, the current goes in the same direction on the positive side as on the negative side, and it will flow in this line impedance stabilization network through this center point to the ground, as well as here. So if you look at the sign convention here for the voltage 1 and voltage 2, you see if the red arrow points upwards, so the V2 is positive as well as V1 is positive. So the actual common mode voltage that you have there across the 50 ohm resistor is V1 plus V2 divided by 2. A bit different is for the differential mode. The differential mode is the more common known current. It flows as a loop, and you can see here it's positive, leading to a positive voltage here, and kind of a positive voltage from the minus to plus, but negative voltage plus to minus. So you have to, in this case, subtract the voltages, and like this you get the differential mode noise. If that was too fast, there is a source where I also took the image from, so you can read more about this. However, when you do this and you measure the voltage as shown here, and then you plot in this case, the common mode emission on a logarithmic plot as shown here, and we see here we use decibel microvolt as the unit. You can see here the common mode noise at different frequencies, and you see here at very high frequency you have quite high common mode noise. Now the objective is that you never, or your total emission never is above a certain limit, which is given by their different standards out there. This is the CISPR 25 example I show here. And if your system crosses kind of this limit from the reference, you have a problem and you have to do something against this. And in this particular case, what you need is a common mode filtering. And what you often do is you use a common mode choke. So in a way of inductively filter common mode currents. Let's look at this picture here. So this is basically how you wind a common mode choke. You have two windings. The one in the positive, this could be here on the positive side, and the second one here that would be connected down here between the lesion and this bar. So if you look at different kind of currents, let's say you have a differential mode current, the current goes here, then to the system and here back, and then you, with the right hand rule, draw the direction of the magnetic field. You will see that differential mode currents lead to, on the positives on the top side, a flux direction in this direction and a flux in this direction on the negative side, and they are canceling each other out. So in other words, a differential mode can more or less, or ideally, freely pass the common mode choke. It's not affected by common mode choke. Now for the common mode current, that's the current you actually want to block. It's the exact opposite. A current leads to a flux direction like here, as well as here, the same flux direction. So you have a very high impedance if there is a common mode current. A high impedance means filtering out the noise. And that's basically your objective. So what is the issue? Well, that's what I just said. You have a high impedance for common mode and a low impedance for differential mode. Now, from a magnetics modeling perspective, this is quite interesting because of the usually dominating or always dominating differential mode current. You have a relatively small flux quantity here in the common mode choke. Because of this, you have relatively low core losses, but at the same time, you have high winding losses because the whole current, like the operating current, actually flows through this component. So you have to account for high winding losses. And to model the common mode current is difficult, especially if you have no prototype yet built. And the reason is, on one hand, if I go back, you usually don't know these stray capacitance. It's heavily dependent on your PCB layout, on many things that are difficult to model. So it's very difficult to model this current. Usually it's measured, or it can be approximated by some rule of thumbs. So what we did, we have developed an approach that enables designing a common mode choke based on estimated common mode emissions. Or you can also measure first and then let the tool choose you a common mode choke. With this, I would hand over to Marcos because he's the originator of this approach, so he will present this.
Okay. Can you see my screen, Jonas? No. Okay. Perfect. Yeah. So yeah, thank you, Jonas, for the theoretical explanation of the common mode chokes. Okay. So what we are developed during these weeks is a feature. Okay. For the moment, it's on beta version, let's say, which is called common mode choke designer. Basically, how it works. Well, for the input specs, it's use the same specification that that you apply in Frenetic AI. So the input voltage, output power, and there is mandatory to put the switching frequency, which is different between the when you design the converter with the switching frequency could be variable. Okay, so here it's mandatory to have it, and then there is two ways to let's say designing the common mode choke. The first one is because most of you, or also included me, when you're designing a converter and you don't know exactly which is the straight capacitance and which is the what is the common mode current, okay, you can just consider to modeling, but it's very difficult, okay. But then you need to measure this common mode current. But typically, what you need to have like a first filter, okay, because if not, sometimes this common mode noise could be, let's say, be a bad part, a bad component of your system, okay. So usually what you take is, well, a common mode choke for another design, or maybe for a reference design or something like that. So here, if you don't specify any impedance, what we apply here is general rules based on information from different, let's say, reference designs for different real designs, okay, that you can find in the market. For example, in automotive, some 11 kilowatts or 22 kilowatts OBCs, and so on, and apply some rules depending on the frequency and the impedance that you need to reach or to comply with the standards. Okay. After the design of the common mode choke, you need to check in Frenetic Simulator the loss and the temperature to see that everything is fine. And if the temperature is okay, the next step is to build the prototype and test in circuit. Okay. And then when you measure the common mode noise, you can see how you are. Okay, so if the noise is in the limits, okay, it's good. You have your final common mode choke. But if it's not in the limit, you need to adjust the impedance requirement. And then this is the second way to designing with a common mode choke designer, which is selecting the impedance that you want on a certain frequency. So to show that, let me go into to the web. Okay, so this is the future. Okay, this is a beta interface that we would like to implement if it is interesting in the Frenetic AI interface. And basically here what you have is well, the topology selection, the power. Let's do, for example, a PFC for an 11 kilowatt 3-phase PFC. So we have third part of the power. The input voltage could be the AC universal input voltage. We can put the nominal, and the switching frequency we can specify 100 kilohertz. So the output voltage could be 390, 40, 400. So as you can see here, this is optional. If you don't write anything here, you can just click on Suggest CMC, and then the tool is starting to analyzing the specification. And as I commented, then it takes into account the topology and also the switching frequency and the power. Just for clarification, when we are talking about topology, for example, in the PFC and the flyback, we are talking about topologies that has AC input, okay, only for these two. So this is the common mode choke that you put in the AC part. But for back boost and phase shift full bridge LC converter, which the input is DC and the output is DC, we are talking about the common mode choke that you typically place on the output part, okay, for the DC link. So in both cases, the process is the same. The only change is that the calculation of the current, which in the AC part is the RMS current to calculate the winding losses, and in the DC part is just the DC current that you have. Okay. So this take a couple of minutes, and to don't waste your time, here I have the results. Okay. So basically, this is what the tool shows you, which are different options. The cores that we have right now are Baku-NetSmell from Baku-NetSmell. Okay, we would like to implement more if it is interested, but for the moment we only have the typical ones from Baku-NetSmell. And as you can see here, we have different options. The criteria here is to have, if I remember correctly, around 2.2 millihenries at 100 kilohertz. Okay, and as you can see here, the three solutions meets the requirement. And also another requirement is to, taking the number of turns, seeing if it is fit inside the core, and also for the diameter of the winding, see if it is proper or not for the current. And once you have this, you can go through Frenetic and starting a new design. Okay. And basically, well, here we don't have any common mode choke option, but essentially common mode choke is a transformer. Okay. With coupling near to 1. And if you use the custom option, then here, well, specifying the turn ratio 1, and here you can fill the input specs. The tool, it's intended to use with ambient temperature of 60 degrees. For the magnetizing inductance, it doesn't matter. You can put any value that doesn't affect to the waveforms. Okay, and in the switching frequency, if we are talking about an AC common mode choke, the frequency of the signals are typically 50, 60 hertz. And if we are talking at DC, it's DC. So in this case, we need to put a small value. Okay, we put 100 hertz because the materials that we have here needs the minimum of 100 hertz, but it doesn't matter. Okay, you put a very small value, it's fine. And that's only consider the conductive losses of the winding. For the waveform type, the same. You can use, for example, sinusoidal. If you are in DC current, you can take the RMS value of the sinusoidal and use it as the DC current, okay? So here, if you put the duty cycle, it doesn't matter, 0.5. And here, the voltage peak to peak to just check the conductive losses needs to be very small, okay? Because as Jonas commented previously, the core losses are very, very small, practically are 0 in most of the cases. Okay, so if you put a very small voltage peak to peak, the tool just consider that the magnetic flux density is very small and the core losses are practically 0, and you have only conductive losses. For the peak to peak, well, we need to put here, in this case, the 18 amps of RMS. So if we do a quick calculation, 18 multiplied by the square root of 2, multiplied by 2, we have 50.76, and we have here the RMS, which is almost 18. Okay, so you are ready to simulate and check one of the solutions that we have here. Okay. Well, before that, and this is something that we are right now currently fixing. Okay. Well, here in Frenetic, you have the nanocrystalline material, and here the typical case is to choose a toroid, okay? But before that, there is a bug in the winding, so you need to do a quick trick, which is basically take ANCC shape from any, it doesn't matter the shape, okay? And here you can write the number of turns of one of the solution. Let's take, for example, this one, which is 10 turns. We can go here, 10 turns, go to the winding, put 10 turns in the primary and in the secondary sign and click on suggest wire, okay? And don't pay attention of this. So then when you do that, you are able to design in the, or to check the common mode choke, okay? So basically you need to, first of all, search with this parameter, okay, that I have here, the result. Well, let me to check quickly, 1 second, because this, okay, so here, sorry, it's 424 Acconet smell. Okay, so here we have the data of the core. Okay, so it's almost 40. Yeah, if we consider also the isolation is 40 millimeters of the outer diameter. So if we go here, we can choose the three. Okay, is this one, the 342.3, 22.3, and then if we click on run core only, what we will see here is more or less the inductance that we are looking for 100 kilohertz, but this inductance is a fixed value. So please consider this inductance as the final inductance, okay, which this one is the ones that it's provided by the dataset of the material and of the core. And here, as you can see, the magnetic flux is, or the flux density is practically neglected and it's 0. So then we can go to the winding and here select the round wire and put the strand diameter, which in this case is 1.6, yes, with one parallel. And here in the primary side the same. So we can put the round 1.6 and then click on run. This part, which is in Frenetic Simulator, probably in the final version, if finally we will release it, we can integrate this part directly to the Frenetic AI. So in this process of, let's say, selecting the core and selecting the different solutions, we also run in Frenetic Simulator to check directly the maximum temperature and the losses, okay? But for just to show you how the process it works, we finally get here the maximum temperature, which in this is 120, and the total losses, which is 5 watts, okay, which as you can see here are basically winding losses, which is if you multiply the RMS with the RDC, that's what you probably will get, okay? And yeah, that's how the process works. So as you can see here, well, you can choose between the different options depending on the size. This is a factor which is the copper factor. The lower the copper factor, the higher the size of the core typically, okay? Because this part, it takes into account how the winding is filled, okay? Regarding the winding, okay? So as you can see here, we follow some rules to ensure that when you go to prototyping this, you will get something which is visible for the assembly point of view and not something that is not possible to assembly. And yeah, that's basically how it works. And here, well, as Jonas commented previously, we provide a questionnaire to for all of you. It's anonymous, so if you can, I don't know if the link is on the chat, Jonas, but maybe we can.
Yeah, we'll put it in the chat now.
Okay. Okay.
Maybe it's a bit, yeah, I think it works. Yeah. Thank you, Marcos. Just two things I would like to say. So this is now working, like Marcos showed, kind of a process that has a lot of breaks, right? You need to have one tool, then you have to do them manually in another tool. But I think with this, you showed two things. You can already today model common mode chokes in Frenetic Simulator, so it's possible. But of course, if we integrate this in Frenetic AI, then we want to have a kind of a seamless integration, so it would not lead to all these breaks that you have seen now. generally, we would really appreciate this form. Takes maximum 3-4 minutes to fill out. If you could take the time, fill this out, and well, let us know anything we should know, because we would like really to develop something that has some value to people, to the market, basically. I think we can now take some questions. Let me see whether there were some questions. There was one question I've seen a bit earlier. Do you plan to integrate other converter topologies for the CMC sizing? Yes, we do. That's the first step. We already have more topologies in Frenetic AI than in this little tool. But also fill out this form, and if you have a specific topology, which actually the form doesn't ask you for that, but write it down anyways. It's all anonymous, but write us down which topology you would like to see, and we can also shape the tool according to your need. Okay, I think there are no questions otherwise. I assume everyone is trying to fill out the Google
There's
Forms.
a new question, Jonas.
Are there examples for three-phase applications? We are considering integrating three-phase topologies in our systems. Currently, we have not done this, but that's mainly a bit the reason is where we're coming from. We're more from the switch mode power supplies market, but we will, but probably not in the first round, integrate three-phase.
Yeah, but in the future, I think that is also possible to integrate maybe a four-winding common mode choke also, because the process at the end is the same, okay? And in Frenetic Simulator, you can also simulate four windings instead of two. Okay, what about the common mode chokes in input side of the CDC converter? It's the same, okay? I mentioned the output side, which is what I find, but also in the input side, it works similar, okay? Maybe what we can do is to put a way to indicate where's placed the common mode choke, if it's on the output or is it in the input. The only thing that changes is because it takes in, when to calculate the current, you take the input voltage and you take the output voltage, or you take also the output power, okay? The only thing that which is in the input voltage, we need to apply some rules of efficiency, because, for example, in a flyback, you don't have a 90, or it's very difficult to reach 97, 98% of efficiency to consider that most of the output voltage are part of the input voltage and that you don't have any loss. So in this case, maybe we can integrate something that you can indicate where it's placed, okay, in the input or in the output side. How to define common mode voltage rating and how to implement the right isolation. Okay, and the second question is also kind of the same, creepage and clearance distance and pre-safety standards. For the moment, to meet typically the creepage and clearance distance, okay, I don't know, well, I can go to the first slide. Well, if you see this component here, okay, there is a plastic, okay, this is more for the mechanical part, okay, not for the designing part, which basically you have a plastic part here, which needs to be together to the core, okay? So in this case, that's acting as a barrier to keep the creepage and clearance distance in this direction, okay? So here you have this, and this one you have the plastic part, okay? But this is typically something that you consider more in the mechanical part, okay? And in the tool, or in the designer, what I consider is don't fill all the window, okay? So have enough space here to put this plastic barrier, okay? What's common current flows through a converter?
How much will the tool consider about interwinding capacitances? Well, not today, but these are things. It's very important. Fill out a survey and write down. You would like to see the interwinding capacitances. We are developing the tool. It's under development. So, I mean, our idea is to add this, but write it down, so it increases. We see that the market asks for that.
And how much common mode current? Typically, is in the order of microamps. Okay.
I missed this one. Yeah.
Mm-hmm. Yeah. So it's not a big, let's say, current like the differential mode current. Okay, and it's in the order of microamps, and depending also on the frequency and so on.
All right. Florian asked they could support us with the right magnetic force. Yeah, reach out to us. We are happy to have a discussion. I think the webinar was planned for 30 minutes, so we will stop. We don't want to take more time from you.
Okay.
Just we would really appreciate if you fill out this form. It takes 3-4 minutes. Whatever you question, you can also ask questions in there. Thank you very much for attending. Reach out to us if you have questions.